One topic that's important to discuss in R is the question of, when a function sees a symbol in its body and it's executing inside the R environment, how does it assign a value to that symbol? So, for example, take a look at this function here that I've defined called lm. So lm here is a function which takes its argument x and it multiplies it times itself. So you can think of it as squaring the input. Now there's already a function in R called lm. So I've created a function here also called lm. So when I call lm in somewhere else in R, maybe in another function or something like that, how does R know what value to assign to the symbol lm? So it sees the symbol lm, and how does it know whether to call the function that it just defined here or the lm function that's in the stats package that's used to model, to fit linear models? And so the idea is that R needs to bind a value to a symbol. So in this case, in the previous slide, the symbol was lm, and it needs to bind a value to it. And the value is going to be a function of some sort. It's either going to be my function, or it's going to be the function in the stats package. And so when R tries to bind a value to a symbol, what it does is it searches through a series of environments to find the appropriate value. So environments are you can think of them as lists of objects and values, or symbols and values. And so when you're working on the command line and you need to retrieve a value of an R object, basically what happens is, the first thing that happens is you search for the global environment for a symbol name matching the one requested. And so for the global environment, it's just your workspace. It consists of all the things that you've defined or loaded into R. And so if there's a symbol there that matches the name of the one that you're requesting, then it will take that symbol and then retrieve the value that's associated with that symbol. So in this case, I defined lm in my global environment, and so because that exists, if I'm working at the command line, when I call lm, it's going to find that object first. So if there's no match in the global environment, then what happens is the R will search the namespaces of each of the packages on the search list. So if you look at the search list consists of all the R packages that are currently loaded into R. And so you'll see that there's an order to the search list. And it starts at the first element, which is the global environment. That's number 1 on the search list. That's always number 1 on the search list. Then you can see second on the search list is the stats package, and the graphics package, the GR devices package. All the way down at the very end is the base package. Okay, and so somewhere in this list of packages, R is going to look for a function called lm. And of course, if it's not in the global environment, then it will eventually find it in the stats package, which is the function that's used to fit linear models. So, as I said before, the global environment is equivalent to the user's workspace, and it's always the first element on the search list. And furthermore, the base package is always the last element on the search list. So clearly, because of the way that the search process works in terms of going down the list of packages, the order of the packages on the search list matters. And furthermore, users can configure which packages get loaded when you start up, and users can also load packages whenever they want. So you cannot assume that there's going to be a set list of packages available, or that the packages will be in any sort of order. So they can be in different orders at any time depending on what the user has decided to do in a given session. And so when a user loads a package with the library function, what happens is the namespace of that package, which is the environment that has all the symbols and all the values for those symbols, the namespace of that package gets put in the second position of the search list, so right behind the global environment, and then everything else just kind of get pushed down one level. And then the search will kind of go down. Will include that new package, in addition to all the other packages that were originally on the search list. One thing to note is that R has separate namespaces for functions and non-functions. So it's possible to have an object named C somewhere and then a function named C. Of course, in your global environment, there can only be one symbol named C. But it's possible to have, for example, a vector named C, and that won't necessarily interfere with the function that already exists that's also named C. So this leads us to the scoping rules for R, which I think is the main feature that makes it different from the original S language. So since most of you probably did not use the original S language, this may be something of a moot point. But the point is that the scoping rules are are essentially what makes R different from the original. So what are the scoping rules? So the scoping rules determine how a value is bound to a free variable in a function. So if you're in a function, there's two types of variables. There's the function arguments that are passed through the definition of the function, and then there may be other variables or other symbols that are found in the function that are not function arguments. And the question is, how do you assign a value to those symbols? And so R uses what's called lexical scoping or static scoping, and this is a common alternative to something called dynamic scoping. And so this is related to the scoping rules is how R uses the search list to bind a value to a symbol. And one thing that's nice about lexical scoping is that it turns out to be particularly useful for simplifying things like specifically statistical calculations. So take a look at the following function. So this function has two formal arguments. They're called x and y. And the body of the function, basically, it squares x and it adds the ratio of y divided by z. Okay, so x is clear and y is clear, but where did z come from, right? And so in this case, x and y are formal arguments, but the symbol z is what's called a free variable because it wasn't defined in the function header. And so the question is, well, what value do we assign to z, assuming that values were inputted to the function for x and y? And so the scoping rules of the language determine how we assign a value to something like z, which is a free variable. So if I were to, so this lexical scoping, the rules in R can be summarized by the following sentence, which is basically the values of free variables are searched for in the environment in which the function was defined. Okay, so think about that for a second, maybe repeat it a few times. And so what's an environment? An environment is a collection of symbol value pairs, right? So x is a symbol and 3.14 might be its value. So every symbol has a value bound to it, and you can think of everything in R as being pairs of symbols and values, right? So another symbol might be y, and its value is a data frame, for example. And so every environment, which is a collection of these symbol value pairs, has a parent environment. So it's kind of like the environment that sits on top of it, that it inherits from. And it's possible for an environment to have multiple children. So there might be one parent environment and many children environment. And so there's only one environment without a parent, and that's the empty environment. And so R uses a lot of these types of environments. So you think of the global environment, which is your workspace. That is a set of symbol value pairs, right? So you have a bunch of things that you've created in your workspace, and they all have names, and each one of those things has an object associated with it. So they might be a vector of numerics, or it might be a data frame, or it might be a list, or whatever. And so there are all kinds of these. Each package has a namespace, and that's like an environment. It has a bunch of symbols and values associated with it. And so the key thing in R is that if you take a function and you associate it with an environment, then that creates what's called a closure or function closure. And these closures are key to a lot of different types of interesting operations in R. So if you're in a function and you encounter a free variable in that function, what happens? So the first thing you look for is the function in which the environment in which the function was defined. So, for example, if the function was defined, if I defined a function in the global environment, then the global environment is the function's is the environment in which the function was defined. So if I see a free variable in this function, what's going to happen is that if I can't figure out a value inside the function, then I'm going to look in the global environment because that's where the function was defined. If I can't find something in the global environment, then the search continues in what's called the parent environment of the global environment. And so and what happens in the usual case, if I define a function in the global environment, then the function is defined in the global environment, and then its parent environment is the next thing down on the search list. So what happens is that you just go down the search list until you eventually find the value for this free variable. Now, it's possible to define a function outside of the global environment, and so generally speaking, what happens is that a function will look for a value in the environment in which it was defined, and then it's going to look, if it can't find it there, then it's going to look for the parent environment. And then if it can't find it there, the search it will keep looking at the parent environment or the parent, etc., until we hit what's called the top level environment. The top level environment is usually the global environment. However, if the function is defined in a package, then the top level environment is the namespace of that package. If you can't find a value there, then once you hit the top level environment, the search will continue down the search list until we hit the empty environment. So after the base package, for example, then we hit the empty environment. If you can't find a symbol in all these environments and we've hit the empty environment, then we throw an error saying we can't find a value for this symbol. So why exactly does all this matter? So it's not immediately clear. No. So typically a function is defined in the global environment so that the values of the free variables are just found in the user's workspace. So this is kind of the right thing to do. It's kind of what most people are expecting. If you can't find a value inside the function itself, you just look in the global environment. So this is the idea here is that you can define things like global variables that will be common to a lot of different functions that you might be defining in your workspace. But the key difference in R is that you can define functions inside of other functions. And so, for example, a function can return a function as its return value. So in most functions, they'll return a list or a vector or a matrix or a data frame or something like that. But it is possible for a function to return another function. And then if that's the case, then the function that gets returned, it was defined inside of another function. So it's the environment in which it was defined is not the global environment. It's really it's really the insides of this other function. So this is when things get interesting, and this is when the scoping rules really have an impact on what you can do. So I'm going to define a very simple function here. And often these kinds of functions come in the form of what you might think of constructor functions. So the idea is that the function is constructing another function. So here's what I want to do. I want to create a function that defines another called make.power. And what make.power takes as input is a number n. Okay. So, and inside the make.power function, I define another function called pow. And pow is going to take an argument called x. And so what's going to happen is that the pow function is going to take the argument x and raise it to the power n. Okay, and so make.power returns the function pow as its return value. And so you can see inside the pow function, x is a function argument, so that's not a problem. But n is a free variable because it's not defined inside the pow function. However, n is defined inside the make.power function, and so since that's the environment in which pow is defined, it will find the value of n. The pow function will find the value of n inside that other environment. And so what happens is that I can call make.power and pass it a number like 3, and then it will return a function which I'll assign to be called cube. So, and similarly, I can pass 2 to make.power and then create a function that I'll call square. So now when I pass cube the number 3, what it does is it raises 3 to the third power, so I get 27. If I call square on the number 3, it raises 3 to the second power, so it gives me 9. And so so now I've got one function that is capable of constructing many different types of functions, and by raising them to various powers. So how do you know what's in a function's environment? So you can look at the function. So you can look at the environment in which the function was defined by calling the ls function. So if I call ls on the environment for cube, you can see that inside the cube function there's an object called n, and if I use get on n, you'll see that the value of n is equal to 3. So that's how the pow function knows to raise it to the third power. Excuse me. That's how the cube function knows to raise the argument to the third power, because it's already defined in its closure environment. Similarly, the environment for square, you can see it has the exact same objects in it, but now the value of n is equal to 2 in the square function. So I want to make one brief comparison between lexical scoping, which is what R does, and dynamic scoping, which is what maybe some other programming languages implement. So here I'm assigning the value of y equal to 10, and then I'm creating a function f, which takes as an argument x, and then it assigns y equal to 2, it squares y, and then adds g of x. So what's g? G is another function which takes as an argument called x, and it multiplies x times y. So in the f function, y is a free variable, and g is also a free variable. So the g function is not defined inside of f, nor is it an argument to f. And then in the g function, then the symbol y is a free variable. And so the question is, if I call f of 3, what gets returned? So with lexical scoping, the value of y in the function g is looked up in the environment in which the function was defined, which in this case was the global environment, so that the value of y in the g function is 10. So with dynamic scoping, the value of y is looked up in the environment from which the function was called, sometimes called the calling environment. So in the R, the calling environment is known as is what's called the parent frame. In this case, the calling environment, y was defined to be 2, and so the value of y would be 2. So calling the function f would produce different answers depending on whether you're using lexical scoping or dynamic scoping. So the one thing that will make lexical scoping and dynamic scoping look the same is that when a function is defined in the global environment and is subsequently called from the global environment, then the defining environment and the calling environment are exactly the same. And so this can sometimes give the appearance of dynamic scoping even when it doesn't exist. So here I've got a function called g. It takes an argument x. It assigns a to be equal to 3. And then it adds x plus a plus y. So in this case, x is a formal argument. A is a local variable, so it's not a formal argument, but I defined it inside the function, so that's okay. And then y is a free variable. Okay. So if I call g of 2, the function g is going to look for the value of y in the global environment. If I haven't yet defined y, then there has to be an error because it doesn't know what value to assign to the symbol of y. So that's what I get in this line here. Now, if I define what y is, I say I assign it to be 3. If I call g of 2, then it returns 8 because now it's able to find y in the global environment. So even though it looks like the value of y was looked up in the calling environment, it's actually the defining environment because g happened to be defined in the global environment. So there are a number of other languages that support lexical scoping. Some examples are things like Scheme, Perl, Python, and Common Lisp. And of course, there's a well-known computer science theorem, which is that all languages eventually converge to Lisp. And so it's not an obscure type of feature. It's actually very common in a number of other programming languages. So one of the main consequences of lexical scoping in R is that all the objects have to be stored in memory. So if you're working with a programming language that has very small objects, this is generally speaking not a big problem. But because of the nature of the scoping rules and because of the complexity of the different environments and the way that they're all linked together, it's difficult to implement this kind of model outside of physical memory. And so the consequence was that when R was originally designed, everything was stored in memory. Things are getting complicated now because we have very large types of data sets, and being able to read them into R is a challenge if everything has to be stored in memory. Second, so every function has to carry a pointer to its defining environment, and that defining environment could literally be anywhere because there could be functions within functions, and if one function returns another function, then there has to be a pointer to that piece of memory where the defining environment is stored, and so this makes the model a little bit more complex, but all the more useful. So in S+, which was the original kind of implementation of the S language, the free variables were always looked up in the global workspace. So everything could be stored on the disk because the defining environment of all the functions was the same.